In today's video, we're going to look at section 6.4, which is conditional probability. We're going to do the first half of it in today's video and then the second half in tomorrow's video, where we're going to look at more independence. So what happens if these events are independent? But right now we're just going to look at conditional probability. I'm going to show you what this means with an example. So in this example, we are told that there are 50 students in a class. 30 of those students are freshmen, 22 of those students are math majors, and 8 of those are neither freshmen or math majors. Okay. We're going to look at a couple things with this, but whenever you are given that information, the first thing I want you to do is draw a Venn diagram. It's way easier to see what is actually happening when we draw a Venn diagram. This takes us back to chapter 5 when we looked at Venn diagrams. So we know that there are 50 students in the class and 8 of them are neither freshmen or math majors. That tells me that 42 people in this class, 42 people are freshmen or math majors or both. So I know that within the actual Venn diagram circles for freshmen and math majors, I need a sum of 42 people. Okay, and there are 8 people that are still in my sample space of my 50 people in my class, but they are not freshmen or math majors. So I have to split these 42 people up. Now I know that 30 of them are freshmen and 22 of them are math majors. If I add those together, I get 52 people. Well, I only need 42. So that tells me the difference between 52, which is the sum of the freshmen and the math majors, and the 42 that I actually need, the difference in those is 10. So I know that my overlap here in my Venn diagram must be 10 people. So always start with that. Look at how many people you are given, the 30 freshmen and the 22 math majors, but we know that we have to fit those 52 people into 42, telling me that I must have an overlap between the two of 10 people. Then the rest of it's easy to fill in, okay? Within my freshman circle, I need 30 people. I've already got 10, so that tells me that there are 20 that are freshmen but not math majors. And then I need 22 people in my math major circle. 10 of them have already been used up in the intersection, telling me that there are 12 people that are math majors but not freshmen. Now we can go ahead and look at the problem. There's 2 things we're going to look at here. The first thing is the probability of being both a math major and a freshman. So I am looking at here the probability of being a math major and being a freshman at the same time. Okay. The probability of picking any one of these students is equally likely. So that will take me back to what we were looking at before. Because all outcomes are equally likely, I can do this by looking at the number of people that are in that intersection divided by my total number of outcomes, my total number of people. Well, the number of people in the intersection was 10. My total number of people was 50. So that leaves me with 1/5. Then I want to look at the probability that the person is a math major given that they are a freshman. This leads us to conditional probability. We are looking at the probability of an event happening under the condition that we already know that there is another property. So we've already been given a condition that that person has to be a freshman. And we are looking at the probability of another event happening given that that event has already happened. Okay. That is what conditional probability is. It's finding the probability of an event happening given that, under the condition that, we already know that another event has happened. Okay. So here, we know that we are looking at freshmen. We're not interested in anyone that is not a freshman. We are looking at, given that the person that was picked is a freshman, so we are just looking at the 30 freshmen here. What is the probability that they are a math major? Okay. Well, I know that 10 out of those 30 people are math majors. So the probability of being a math major given that they are a freshman. And the way that this is written is the probability that someone is a math major with a line given that they are a freshman. So whenever you see one of these problems where you have the words given that, put a line, or under the condition that, we put a line. So it's the probability that someone is a math major given that they are a freshman. Okay. Well, I know that there are 30 freshmen, so I'm just looking out of the 30 freshmen now. 10 of those 30 are math majors. So the probability that someone is a math major given that they are a freshman is 10 over 30, which is a 1 in 3 chance. So whenever you get one of these probability problems where we are looking at conditional probabilities, it is just the probability of an event, assuming that the other event has already occurred. So here it was the probability of picking a math major, assuming that that person is already a freshman. That brings us to our conditional probability formula. The probability of an event E, given that the event F has already happened, is equal to the probability of the intersection of E and F happening, so the probability of both E and F happening at the same time, divided by the probability of the event F. Here we assume that the event F can happen, so we assume that the probability of F is not 0, because otherwise we end up dividing by 0, which can't happen. But whenever we get one of these conditional probability problems, we take the probability of both events occurring at the same time divided by the probability of the event F that has already occurred. There is a way of simplifying this if you have a case where there are equally likely outcomes. So going back to our previous problem where any of those students are equally likely to be picked, then this thing actually simplifies. Okay. In that case, the probability of the event E, given that the event F has happened, going back to our formula at the top, the probability of E intersect F, taking us back to what we looked at with the probability of an event happening with equally likely outcomes. The probability of an event was the number of outcomes in that event divided by the total number of outcomes. So that would be the number of outcomes in the event E intersect F divided by my total number of outcomes N. So in our previous case, it would have been the number of people that were both math majors and freshmen divided by my total number of people, which would have been 10 over 50. Divided by the probability of F, again, same deal as before. It would be the number of people, or the number of outcomes in F, divided by my total number of outcomes. Okay. That then simplifies because the n's cancel to the number of outcomes in the intersection of E and F divided by the number of outcomes in the event F. So that is exactly what we did in our last example. We had 10 over 30 because there were 10 people in that intersection and 30 people that were freshmen in that event F. They have gone through this full justification like this and said slightly more about it in the textbook if you would like to take a look at that. Both of those are on page 266 and 267 in the textbook if you would like to take a look. But as long as you understand it to this point, I'm happy with that. It just gives you a bit more background to it. Another way that you can look at this problem is by looking at Venn diagrams. Okay. And it's exactly what we did with our college student example. This was the circle that represented the freshmen. This was the circle that represented the math majors. Okay. I am just looking now at the people that were freshmen. Okay, in my conditional probability problem, I was just looking at the people that were freshmen. So the probability of someone being a math major, given that they were a freshman, is just going to be the probability that they fall in the circle M, given that we know that they fall in the circle F. Well, that would just be the probability that they fall in that intersection, given that we know that they must fall in that larger circle. That is where our formula comes from. Okay, you can see that more clearly on our Venn diagram. And like I said, they have gone more into this in the textbook as well. Sometimes they rearrange this formula because they're actually looking for something slightly different. Let's go back to what we had here. Okay. That is the probability of an event E happening given that the event F has happened. Sometimes what they will actually look for is the probability of the intersection. And they will give you the probability for the conditional probability, and they will ask for the probability of that intersection. So all we do in that case is we just rearrange the formula, and that is called the product rule. So that says, again, we're going to assume that the probability of F doesn't equal 0, because otherwise this whole thing will come out to 0 anyway. And it says that the probability of the events E and F happening at the same time is just going to be the probability of F happening multiplied by the probability of the event E given that the event F has happened. So we've just rearranged that formula. I'm going to go through a quick example of something where they have used this product rule, and it's the same for any one of these problems where they need to find that probability of the intersection, but they have given you that conditional probability. Okay. This is out of the textbook at the bottom of page 267. It says that assume that a certain school contains an equal number of female and male students. Okay, so the probability of being a male in this school is going to be 50%. And the probability of being female in this school is going to be 50%. Okay, just so that we have those probabilities. 5% of the male population is colorblind. So the probability of being colorblind, given that you are a male in this school, is 5%. Okay, because it tells us that the probability of the male population being colorblind is 5%. Okay, so the probability of being colorblind, given that you are a male, is 5%. Okay, because 5% of the male population is colorblind. We're not looking at the females here. And it says to find the probability that a random selected student is a colorblind male. So what's the probability that the person picked is both colorblind and male? Okay, that's where our formula comes in. So the probability of being colorblind and male. We know the probability of being colorblind given that they are a male, and we know the probability of being male in this school. So we're looking at the probability of being male multiplied by the probability of being colorblind given that you are a male, which would be those two numbers multiplied together, which should give you 0.025. So you've got a 2.5% chance here that a randomly selected student is both male and colorblind. A lot of this is down to the wording of the problem, so please be aware of that. They will give you the probability of, in this case it was being male and female, or they'll give you the probability of the event E, and then they'll give you the probability of the event F. But then they will give you a sentence that will be something along these lines, where they've said the probability that a male was colorblind is 0.05. Okay, 5% of the male population was colorblind. That tells me that the probability of being colorblind, given that you are a male, okay, we already know that they're male, but the probability of being colorblind, given that you are a male, was 5%. And then it's asked for, what's the probability that I randomly select someone and they are both colorblind and male? And that's where our product rule comes in. The last example that I want to go through here looks at cards. Again, this is a very popular question whenever we look at conditional probability. So it says that we take 2 cards, one after the other, without replacement, out of a deck. Okay, a standard deck of cards has 52 cards in it. Okay, and we are taking 2 cards out of it without replacement. So that means I take the first card and I put it somewhere else, and then I take the second card out. I don't replace the first card into the deck. I'm going to look at the probability. So what is the probability that both cards are red? I'm going to do this by using the product rule. So I want to know, what's the probability that my first card is red and my second card is red? Okay, that's how I'll denote this. By using our product rule, okay, let's say that I know that my first card is red, and then I want to look at whether my second card is red. Okay, so I would be looking at what's the probability that my second card is red, given that my first card is already red. Okay, so I have 2 different events happening here. My conditional probability here would be the probability that the second card is red, given that the first card is red. And then I'd be looking at what's the probability that the first card is red. Okay. Why have I done it this way around? Well, I can't look at the probability that the first card is red, given that the second card is red, okay? Because I have to draw the first card first. So I know that for my conditional probability, I must be looking at the probability that the second card is red, given that the first card is red. So if we effectively look at this in terms of events E and F, the second card being red would be event E, and the first card being red would be event F. Okay? So I would be looking at the probability of E intersect F, the probability of the second card being red and the first card being red would be the probability of the first card being red, because that's my event F. That's effectively going to be the other event, okay? And my event E is going to be the probability that the second card is red, okay? Again, the reason I have done that is because I cannot have the probability of the first card being red given that the second card is red, okay? I don't know what happens with the second card when I'm drawing the first card. So I need to look at what's the probability of the second card being red, given that I know what's going to have happened with the first card by that stage. So what's the probability of the second card being red, given that the first card is red? Okay. let's look at what these probabilities are. The probability that the first card is red. I have 52 cards in a deck, 26 are red, 26 are black. So that tells me that the probability that the first card is red is going to be 26 out of 52. Okay, I can also write that as 1/2 when I simplify this in a second. Then I want to look at what's the probability that the second card is red, given that the first card is red. Okay, I've taken my first card out. Okay, I've already taken out one of the 26 red cards, and I also have taken out one of the 52 cards. Okay, my first card has already gone away, and not only has my first out of my 52 cards gone away, I've also had one of the 26 cards go away because I know that that first card was red. So that leaves me with 25 out of 51 remaining cards are now red when I go ahead and draw that second card. So I've had to take into account that I now only have 51 cards left in the deck, but I've also had to take into account that that first card was red, so I'm left with only 25 red cards for my second draw. So then you could simplify this. I've got 1/2 multiplied by 25 over 51, which would then give you 25 over 102. Okay. So this is the other type of problem that you may see with this, where we're looking at the probability of 2 cards being drawn, and they could be red and black, or 2 reds, 2 blacks, etc. Okay, and you'll have to figure out which one is the event E, which one is the event F, because you have to make sure that you're looking at the probability of an event happening given that there is another event that's already happened. So in this case, we're looking at the probability that the second card was red, given that I know what's already happened with my first card. In our next video, we're going to carry on with this section, and we're going to look at what happens when these events are independent of one another.